Tesla says aluminum-ion batteries stay stable up to 85 degrees Celsius. That's much higher than lithium's danger zone, which starts around 60 degrees Celsius. Even with higher thermal tolerance, sustained gigawatt-scale charging creates cooling, weight, and energy consumption trade-offs that the research flags as major engineering hurdles. The charging infrastructure becomes the real bottleneck here. Today's top public chargers are roughly 250 kilowatts. A 10-minute full charge would require on the order of 1,000 kilowatts or more. That's like powering a small town just to charge one car. Most electrical grids can't handle that kind of sudden power demand. Imagine if everyone in your neighborhood turned on every appliance at the same time. The lights would dim and circuits would trip. Charging stations would need their own power plants or massive battery storage systems. The electrical infrastructure at gas stations, shopping centers, and apartment buildings would need complete rebuilds. Battery cooling systems would need complete redesigns too. Current systems use liquid cooling to keep batteries at safe temperatures, but 10-minute charging would create so much heat that the cooling system might weigh more than the battery itself. These systems need pumps, radiators, fans, and lots of coolant. All that extra equipment adds weight and complexity that would cancel out other benefits. The cooling system also needs power to run. More powerful cooling means the car's main battery has to work harder just to keep itself cool. This creates a cycle where fast charging requires more cooling and uses more power, which creates more heat. Tesla would also need to build entirely new charging networks from scratch. Current superchargers work with lithium batteries, but aluminum-ion batteries might need different charging protocols and equipment. This means Tesla can't just upgrade existing stations. They'd need to replace everything. The chemistry might support fast charging, but the infrastructure and thermal challenges make 10-minute charging unlikely anytime soon. Even if Tesla solves all the technical problems, rolling out new charging networks takes years and billions of dollars. Building charging infrastructure happens much slower than developing new battery technology. But Tesla's boldest claim might be about cost savings, not charging speed or longevity. Tesla projects a 50-kilowatt pack could fall from about $7,500 today to roughly $2,000 to $4,000. A company projection, not an independently audited price. That's a massive price cut that could potentially reduce car prices by 20% or more. This would make electric cars cheaper than gas cars for the first time. The savings sound incredible for car buyers. Instead of paying extra for an electric car, people might actually save money compared to traditional vehicles. Aluminum is everywhere. It's the most common metal in Earth's crust. You can find aluminum in dirt, rocks, and clay all around the world. This abundance should make aluminum batteries incredibly cheap to build. Think of it like the difference between diamonds and sand. Diamonds are rare and expensive because they're hard to find. Sand is cheap because it's everywhere. But raw aluminum isn't the expensive part of batteries. The real cost comes from high-purity processing, specialized electrolytes, new production equipment, and tighter manufacturing tolerances. Making battery-grade aluminum requires purifying the metal to extremely high standard. Every tiny impurity can ruin battery performance. The processing equipment needed for this purity costs millions of dollars per machine. The background research flags that aluminum-ion electrolytes are more complex and may rely on chemicals that are costly or harder to source than expected. Another factor that could erode projected per-pack saving. The problem is that aluminum-ion technology requires completely new factories from the ground up. Every piece of equipment needs to be different. The mixing machines, coating systems, assembly lines, and quality control tools all need redesigns. It's like trying to make pizza in a bakery designed for bread. The basic ingredients might be cheaper, but you need entirely different ovens, tools, and processes. Lithium battery production took decades to scale up and reach current cost levels. Companies spent billions learning how to make these batteries efficient. They built massive factories, trained thousands of workers, and perfected manufacturing processes through years of trial and error. Costs are still falling as factories get more efficient and production volumes increase. If the chemistry and scaling claims prove out, it could be disruptive. But transitioning existing supply chains and factories carries very large upfront costs and time. Tesla would need to build new factories while the current lithium factories sit empty or get sold for scrap value. All the knowledge about lithium manufacturing becomes worthless overnight. Workers need retraining on completely different processes, and supply chains need rebuilding from scratch. Early aluminum-ion prototypes also need more complex electrolytes and specialized components. These aren't simple swaps of one material for another. Electrolyte is like the blood in a battery.